Okay, today class we will discuss two variant. Okay. Up to now, in the previous class we have studied regarding a single wire antenna. What are the modifications we want to make for a single antenna to make it an antenna? And now let us study. First, we will initially start with a two transmission line. Okay, so this is a one wire, this is another wire, a pair of transmission lines. Okay, so this is a pair of transmission sign. Okay, let us apply some voltage to this. Let us study how it is going to be. Okay, so this is nothing but a pair of transmission line up to here. This is a transmission line. So okay, so for this transmission line, if you need antenna or you need straight line want to act as an antenna, compulsorily the structure should be either curved surface or bend surface. Can bend like this. If you bend like this, there is a chance of radiation. There is a chance of radiation. Okay. So this is the thing we have studied while discussing what is the source for radiation, how the waves will get detected. Now let us take two transmission lines, a pair of transmission lines. Okay. So now let us consider a voltage source connected to the two conductor transmission line is connected to an antenna. Okay. So applying the voltage across the two conductors, transmission line creates the electrical field. No doubt, whenever you apply some voltage across any two paired transmission lines, automatically electrical field comes into picture. Okay, so this electrical field is associated with electrical lines of force, which is tangent to the electric field at each point, and their strength is proportional to the electrical field intensity. Okay, so these electric lines of force have a tendency to act as a on the free electrons associated with each conductors and force them to be displaced. Okay, so what this electrical field will do will make the electrons to move forcefully in some direction. So whenever the electron starts moving, automatically the current comes into picture. Okay, so the movement of charge creates the current that in turn creates the whenever there is whenever there is a movement of current, automatically there is a magnetic field. Thus, we are creating both electrical field and magnetical field. That is nothing but electromagnetic field. Okay. So, if, for example, if you consider this a pair of transmission line, this is positive. Okay. So, generally, charge carriers or electrical charge carriers move from positive to negative. Okay. So, here also positive, negative. Here, this is for next half second has cycle from positive to negative. Here also positive to negative. This is how the electromagnetic waves will get detected. Will get both electrical field and magnetical field. So this is how the wave will get detected. Okay, so up to here the waves are bound together. Okay, so the total net value is 0. Okay, so no signal will go out. But whenever you make the structure like this, whenever you bend the structure like this, okay, so the electromagnetic waves comes into picture and it will get detected from the antenna and it will move into the free space. Okay, now let us see what is the current distribution of a thin wire antenna. Current distribution of a thin wire antenna. Okay, so this is your two-wire transmission antenna. This is nothing but let us consider this is a this is an antenna, for example. So you are here, you are providing some supply voltage. Okay, so this is nothing but open circuited. Okay, we know the formula for open circuited transmission line. Open circuited transmission line. For an open circuited transmission line, so Zn is equal to minus Jz naught into cot beta L. So this is the expression for open circuit. Zn we generally will consider it as Pin by In. So it is minus Jz naught into cos beta L by sin beta L. So in this open circuit, the current in open circuit approximately we can consider it as sin beta L. Okay. So how will be the expression for sin beta L? For example, if the length of the wire is 0, so what is the IOC? Simply substitute is a sin 0. Okay, so 0. Okay. Now let us consider let us consider for uh, um, so what is the expression? The expression is IOC is equal to sin beta L. Let us consider for L is equal to lambda by 4. Then what is the expression? current, the current in the transmission line you can represent as sine. What is the value of beta? Beta means 2 pi by lambda into what is the value of L? Lambda by 4. Lambda will get cancelled, 2 ones, 2's, it is equal to sine pi by 4. So when L is equal to 0, the current open circuited is equal to 0. When L is equal to lambda by 2, the current IOC is equal to maximum. Similarly, when L is equal to lambda by 2, okay, when L is equal to lambda by 2, okay, so simply substitute here, I naught is equal to sine into 2 pi by lambda into lambda by 2. Lambda will get cancelled, 2 will get cancelled, sine pi it is 0. Means when L is equal to lambda by 2, the open circuit is equal to 0. Okay. Next, we will take for any other value, L is equal to 3 lambda by 4. Then its value will becomes 1. Next, from L is equal to lambda, the IOC will becomes 0. Okay, means, so if we take a pair of transmission lines, let us consider this is a pair of transmission lines. Let us consider this is the open circuit condition. Let here L is equal to 0. What is the L is equal to 0? What is the current here? 0. Okay, so let us consider this is let us consider from here to here. From here to here it is lambda by 4. From here to here it is another lambda by 4. From here to here it is another lambda by. Similarly, this direction also. Okay. So now substitute here. At L is equal to 0, what is the current? At L is equal to 0, the current is 0. At L is equal to 0, the current is 0. Okay. Next, after traveling a length of pi by 2, the maximum you are getting current is max is 1. Okay. So this is for L is equal to 0 and the current we are getting it is maximum as 1. Okay. Now let us take for the second case. Okay. So for L is equal to lambda by 4, the total length is lambda by 2. At lambda by 2, the current is 0. Again, this will becomes 0. Okay. So, and L is equal to 3 lambda by 4. It is 3 lambda by 4. The current is mag. Again, it will goes here. So, it will becomes 0 and it will goes like this. Okay. The same procedure means, okay. So, whenever a transmission line is open circuited, automatically standing waves comes into picture. Okay, so these are nothing but the standing waves. So nothing but the standing waves. Okay, so this is the current distribution for various lengths. Okay, this is for up to lambda by 4. From here to here, the distance is lambda by 2. Okay, so for example, this is a pair of transmission. Okay, so this is a pair of transmission line. I can once again draw here. This is my one transmission line. This is my transmission line. Okay, so my waveform is like this. Okay, my waveforms are like this. Okay, so this is at L is equal to 0. This is up to lambda by 4. This is also for lambda by 4. This is for lambda by 2. This is for lambda by 2. So if I take a ordinary transmission line like this, will my antenna will radiate? No. What should I want to do? I want to make this bend antenna at some particular distance. Okay. For example, let us, I am bending my antenna here on the top side at lambda by 4 and bottom side at lambda by 4. Tell me. So I am bending. So see here, this is my expression. So this is my lambda by 4. I am bending here. From here to here, I am bending my antenna. Okay, like this. So this total distance is lambda by 4. Similarly, bottom side also I am bending my antenna like this. Why you want to bend? Already in the previous class we have discussed A straight antenna, a straight wire doesn't provide any radiation. Okay, there should be some discontinuity there. What is the main source for a current? Either the charges should be accelerating or deaccelerating. Okay, so in the structures, okay, so this is for lambda by 4 and this is for lambda by 4. Okay, so this is for. So now draw the same waveform. Okay, so at L is equal to 0, what is the current here? The current is 0. Okay, the current is 0. So this is the radiation for L is equal to lambda by 4. L is equal to lambda by. Similarly, this is the radiation for L. So what is this total length? The total length is, here it is lambda by 4, it is for lambda by 4. So the total length is lambda by 4. Means the current distribution for a thin wire, the current distribution for a thin wire of length L is equal to lambda by 2. L is equal to lambda by 2. This is the radiation pattern. This is the radiation pattern. For L is equal to lambda by 2, where you want to bend a order transmission, you want to bend in the stop at lambda by 4 and other lambda by 4. Lambda by 4 plus lambda by 4, it is lambda by 2. So this is the current distribution for a length L is equal to lambda by 2. Similarly, for example, if I want to calculate the current distribution for L is equal to lambda. Okay, where should I want to bend my top transmission line, bottom line? So total length is lambda. So total length is lambda means I want to bend the top one from here to here. I want to bend this because it is lambda by 2, and bottom one is also I want to bend like this. It is lambda by 2. So I will simply bend like this, my antenna like this. Okay, so what is this total length? This total length is lambda by 2, and this total length is also lambda by. Now tell me how is the radiation pattern? At L is equal to 0, the current is 0. At L is equal to 0, the current is 0. At L is equal to 0, the current is 0. Okay, you want to consider the current radiation from here to here. Okay, so this is for L is equal to lambda by 2. Bottom also the same current. Okay, so this is for L is equal to lambda by 2. So this is this curve. What is the total length? The total length is lambda. The total length is lambda. So this is current distribution, sketch of current distribution for a thin wire of length L is equal to lambda. Length L is equal to lambda. Okay, so like this you can sketch for anything. You can sketch. Let us take, for example, if the value of L is very less than lambda. Let us consider. So, for example, if the value of L is very less than lambda. So, how is your radiation pattern? This is your radiation pattern. Here L is equal to 0. Here L is equal to 0. Okay, so let us consider this. This is your radiation standing wave pattern. So this is L is equal to lambda by 2. This is lambda by 4. This is our lambda by 2. This is our lambda. So this is lambda by 4. For example, if L is the length of the wire is very, so this is your length. For example, I have taken this part. Okay, so if the small portion in the top one and bottom portion, then if I bend that, okay, so this is here, the total length L is very less than lambda. My radiation pattern looks like triangle because the length is only I want to consider this portion. Only I want to consider this portion. So my radiation pattern looks like triangle. So this is for L is very less than lambda. Like this, you can create for any number. You can create the radiation pattern for any number based on this explanation. Okay, so for example, you want to you want to draw the radiation pattern for 2 lambda. Where you want to bend the antenna? Where you want to bend the antenna? On the top side, you want to bend for L is equal to lambda. This entire thing you want to bend. And bottom side also you want to bend entire thing. Okay, so for L is equal to 2 lambda, how will be my waveform? Simply like this. I am bending like this. So this is L is equal to lambda. L is equal to lambda. How is my radiation pattern? So this is up to lambda. From here to here it is lambda. From here to here it is lambda. Okay, so my radiation pattern automatically radiation pattern simply it will looks like this. This is for complete one. This is for one complete one. So this is what is the total length? The total length is L is equal to 2 lambda. Like this, you can draw, you can sketch the current distribution of thin wire antenna of thin wire antenna of any length that may be L is very less than lambda or L is equal to lambda or L is equal to 2 lambda. Okay, so depending upon, for example, if any person asks to draw the sketch for L is equal to 4 lambda, where you want to bend the antenna? You want to bend the antenna like this. This is for 2 lambda and this is for 2 lambda. Total length is 4 lambda. You want to draw the radiation patterns. This is very important problem. Sketch various current distributions. Sketch various current distributions for different cases. Okay. So this is the radiation pattern when L is very less than lambda. So when L is L, how is your radiation pattern? The radiation pattern is triangle. The radiation pattern is triangle. So for L is equal to lambda by 2. Okay, lambda by 2 means you want to bend your wire. This is lambda by 4 and this is also lambda by 4. Okay, so the total length is L is equal to lambda by. Okay, so this is from L is equal to 0. From here to here, this is for lambda by 4. And from here to here, this is for lambda by 4. So this is the radiation for L is equal to lambda by 2. So similarly, this is for L is equal to lambda. Okay, so this is for 3 lambda by 2. Okay, like this, you can construct the this is a radiation pattern of a thin wire for any length. Okay, of a thin wire for any length. Okay, so the expression is generally IOC is equal to sine beta L. Okay, so sine beta means 2 pi by lambda, and you can make the length for any I. Okay, so on this you can create. Okay, this is the very important question. Okay, so the question they may ask in your exam is sketch the current distribution. Sketch the current distribution of thin wire antenna of lengths. First one, if L is very less than lambda. Second one, if the length is less than L less than lambda by 2. The third one is L is equal to lambda by 2. And the fourth one is lambda by 2 less than L less than 3 lambda by 4. The fifth one is L is equal to lambda. And the sixth one is L is equal to 5 lambda by 4. Like this. Okay. You can create by bending the transmission line. Okay. So you'll get the standing wave. Based on that, you can draw the current wave pattern.